The previous working group, Daniel Besman from Auterion, showed us how to address the bridge between BX4 and ROS2 with with micro XRCE DDS. Also, a fantastic demonstration. Also, Tom Dixon from Net will discuss about basically the company behind the first standard networks entirely. I want to make a small aside and comment on the book's launch robot operating system, the complete reference. The book has a comprehensive chapter on MicroROS, which appear in volume 7 of this book, and micro all aspect of the stack that put ROS2 onto MCUs. And the MicroROS chapter is a 53-page chapter covering all aspects of the MicroROS stack, from requirements, design, rationales, and architecture to 3 very different use cases. Now, for today, let's see. So here we have John Gentilin. Hello, John, principal engineer from Sony PlayStation. His talk is RosBot with MicroPython. RosBot is an autonomous open source robot platform based on ROS. Python is a complete Python compiler and runtime that runs on the Verb. And also for today, we have here Arnaud, co-founder of Bitcraze, and about Crazyflie, which is a company focused on developing and manufacturing a small quadcopter called the Crazyflie. And he also will explain the potential benefits of the new framework for projects like. So, John, if you have everything. You're on mute?
Yeah, we did.
Okay.
Yeah, sorry about that. Thank you, David. See my screen? Sorry. It's we go.
Yes.
Yeah, there you go.
My internet's very slow today. Okay. Well, hi everyone, and thank you for inviting me to this talk. It's an honor here. What I want to talk about is a personal project I've been working on called RosBots. It really is the MicroROS stack integrated with MicroPython and then implemented on an ESP32 based robot. So, and I'll get into the tools and the why and how it's. So, introduction of myself. My name is John Gentilin. I work for Sony PlayStation as a principal engineer. This here, what I want to show today is a personal project. It's not related to Sony or any Sony product. It's just something I've been why. So for me, this is really about learning the ROS platform and finding ways to interact with my son. So, my tools here were to leverage or remove telecontrol, so depending on the level of people interacting with it. And also I wanted to incorporate MicroPython that can be programmed in a Scratch-like interface, so I can, this is the part of this interacting with this one. Any questions so far? Okay, so to get into the component architecture of this, the form factor of the compute power is based off a platform called 7 years now, really popular in the UK. It's sponsored by the BBC. It comes in a variety, it has a bunch of add-ons to it, and adaptive boards. There's just tons of projects. So I used this before with my son, and I'm just leveraging the same platform now. It's a great little board. Actually, the board I'm using now has price dropped down to $12 recently.
the is simply designed for younger developers. It's really to engage kids. Well, back again, it's with that wide range of adaptive boards. I think it's one of the more popular platforms out there for kids. There's just so much available. Some questions? And I'm using the DF robot micro robot from DF robot. It's a $2 turtle bot that uses the microbit form factor to power it. So it has a lot. It's something far more complex. So it ranges from $32 to $100, and the difference is the add-ons you can get for it: the lifter, the grabber, and loader, and different like cameras you can get for it and stuff like that. So there's a bunch of add-ons like that, and it also really appeals to kids because it comes with these colorful silicone wraps that make it personalized to their bodies. It's really good. The basic unit for $32 comes with an ultrasonic rangefinder, a line following, and IR LED with like the base model. It's on from there. Switch to the next page. So for the microbit board, I'm not using a true microbit board. I'm using a ESP32 version. And the advantages here is the microbit board, even the version 2, doesn't support Wi-Fi. So the ESP32, one, I was familiar with ESP32 programming before I started this project. And so it's easier for me to get on board with this, and also support Wi-Fi. The downside of this board is it really doesn't support the MakeCode, the PXT. It's a Microsoft product. It is the runtime for the MakeCode.org page. So you have to use a different version, but I think they're going to come up with a MakeCode or runtime for this board, so that it's fully compatible with that. Questions? So I have my demo configuration. I have a local Wi-Fi router here, so that wherever I go to demo my ROS setup, the network's always the same. It's a USB powered router that I plug in, gives me my network. I'm not running this today, but I'm using my compute-based, like my laptop or desktop ROS system to do all the pathfinder planning and navigation and stuff like that. Then I have like the 2 ROS nodes that are going to run MicroPython and ROS, and they talk to each other. You have a tele-op controller, remote controller, and then the robot key. And we can program this all through Blockthing, which is a Python IDE, very simple, easy for people to use. And I plan on integrating Google Blockthing into Sony so that you can actually program it in a block-oriented language, low-code format, and then see the Python it generates and automatically upload Python and execute it in the ROS nodes. Questions? So where I'm at with this project, I have it now that it fully compiles with ROS and MicroPython. It'll bring up both a serial REPL prompt so that you can go into on the node. The file transfer mechanism works. You can exchange code from the your development environment to the MicroROS node, and it execute it. What I don't have yet is it wired up. You can't publish or subscribe to any messages under ROS yet. That'll come in a few weeks here. So I need to wire ROS to MicroPython, and then fix the web REPL, so you can connect to the board either through a serial prompt and have a serial-based REPL, or you can connect to it via WebSockets and have a WebSocket-based REPL command prompt, so you can actually program this thing without it being tethered to the computer. Then I gotta adapt the MicroPython version of drivers for things like I2C, so that there's a common driver model for wherever you interface to the low-level drivers for the board. Things I could use help on here is ideas around how to marshal data back and forth from ROS to MicroPython and back. How to define a new message format in MicroPython and have it be able to send those messages from the ROS layer. So, creating a whole new structure. I think I got this nailed down now. Is how when ROS sends you a message and you get the description and how to interact with MicroPython, so that it's in this properly threaded, so it doesn't crash, and you don't have a threading issue with any currently running task. Also, for my ESP32 config, I could use a little help on figuring out if I'm using IRAM and SpeedRAM efficiently. I'm running out of IRAM. And then what I mentioned before is integrate dual blocking with Sony, and then I'd like to get MicroROS to be a Git submodule versus always checking out the code. I've done a lot of change to the build system to get all this stuff working together. Questions so far? Is this? There's two different Visual Studio Code instances running, two Docker containers. One is running my ROS environment, and that's here. So what I'm going to do is I want to start the agent on this side. What I have here, still see me? I have a joystick bit with a microbit port on it. So I want to get this up the serial port. So you can see here on my MicroROS agent session, I've got a participant that's logged connected to the MicroROS layer here. So now that my node is connected to the MicroROS layer, I could start up so what this has done now is it's connected to my board. At the web REPL pump here, so I can just type in a command. So I'm running Python code here. This here is all the code sitting on my ROS device now. So I can come up here and I load up by defining a function called hello world and say print hello world. Now if I decide to run that, it prints hello world right in my prompt here. So I'm actually interacting with my ROS node live through this IDE. So I can just type in any code. the model I'm thinking of here is very basic. ROS, you can in your so the way MicroPython works, you have Python. It gives you all the things you want to do, all the messages you want, and define the MicroPython entry point you want called when that message arrives. The ROS layer will receive that message description and then forward it onto the MicroPython layer to execute that. Then you have within MicroPython you have full control of all the I2C and IO pens and stuff like that to do whatever you want with the message that comes in. So that, and then you can also publish a message.
How difficult to find C library is like low level codes from C library. And there's the block.
There's a whole process to there's a lot of boilerplate code, and inside the micro. So in MicroPython, there is either a C or a C++ example, and so this is the boilerplate code. The interface is a CPP function, which does some math and returns something back. And here's how this is the code how to register a function. You have to. I don't know if you ever work with MicroPython here, but there's a lot of assumptions around like these. MicroPython ROM Q strings, which stands for unique strings. It's the name of the string here is the characters after the underscore into this Q string thing. So it's you gotta get used to the macros that are in there. But it's pretty easy once you get it down. And then someone else has written a MicroPython wrap product, which is a bunch of templates that will actually take care of a lot of the boilerplate.
Wondering. So you were mentioning that you can subscribe to messages and publish messages. So is this something where you're using RCLC, or is this, so to say, a new front-end library where you are directly using RCL layer?
Yeah, so I have two threads in this product. One is running the ROS layer, and the other one is running a MicroPython. So I have a interface file that'll allow me to subscribe to messages at the ROS layer, but is also bound to MicroPython. So when you say register callback for say command velocity, you register for that callback in a table registered for that message coming in. Here's the MicroPython function you want to call back. And then when that message comes in on the ROS side, it'll actually create a MicroPython task and in a thread-safe way, publish it back in the MicroPython layer.
And are you using for this the RCLC library as in MicroROS, or are you using directly RCL?
Oh, I think I'm correctly using yeah. Still on the education mode on MicroROS. What I did was I started out with the.
So you also you're calling RCL wait and RCL take yourself.
No, I'm spinning.
So you're calling RCLC executor spin something.
Yes, exactly.
Okay, so you're using RCLC.
Yeah.
So
This is all based
on RCL.
Yeah, this is all based off the one of the original in the ESP32 version of MicroROS, it's one of the examples that changed.
So yeah, so answer your question is it's the application called MicroROS. It calls out to the C client.
Yes, yes.
Okay. As we, I'm just short, maybe just some feedback. As we have developed this RCLC layer. Any feedback? Do you find it intuitive, or do you see something that should be improved, or you found it easy to integrate into MicroPython? Is there something we could do to improve the usability of it?
Yeah, the biggest thing that I went for this whole project was getting the build system. I found the MicroROS build system, and even the CMake version of it for MicroPython, to be, as you integrated them together, what you thought was a simple change ended up changing everything. Like, for instance, so the way I've implemented this is MicroPython is a submodule, and I'm taking it straight out of Git, putting it in my project, and then I have what's a expressive IDF component. This is the interface logic from ROS to MicroPython. So if I go in here and CMake this thing, there's one of the CMake files, there's a call to an expressive IDE add component for the networking. And if I take that out, all the rest of the CMake macros tend to fail. The define external project that's compiling the MicroROS library, that tends to fail. I forget which CMake file that was actually. Oh, right here. This is it. If I take out this IDF component register, then this external project add macro fails, as CMake doesn't know what this function is. It's really weird because it's a built-in function for CMake. So it's where I had most of my issues in integrating MicroPython is systems. But as far as MicroROS goes, I would say that the learning curve was good. It was easy. It was a lot of new stuff to me about sending messages and stuff. But it was once I put some time in to learn it was easy. There's no other questions.
Yes, so thank you very much, John, for the demo. Very interesting. Thank you.
Yeah.
So now is the turn of Arnaud. Yes, okay. So perfect. Yes. Right. Go on. Thank you. See the slides. Yes, perfect. So yes, thanks for having me. My name is Arnaud Taffanel. I'm working for Bitcraze. I'm gonna talk about Crazyflie, which is our main product, and more precisely about the current and future communication stack. What we are and will be working on to improve the situation. So Bitcraze is a small company based in south of Sweden. We're in Malmö, just in front of Copenhagen, Denmark.
We are 6 people so far, and we are mainly developing the Crazyflie and ecosystem around Crazyflie. Much as possible to only open source stuff. So all our software is open source and everything is open and documented so that people can use our products for whatever they want. That's our goal. We started as a hobby project. I'm gonna show some pictures of the very first Crazyflie later. In 2009, actually, so quite some time ago. The company was founded in 2011, and Crazyflie 1 was manufactured and sold around 2013. And then we improved that into Crazyflie 2, which is a series we have right now, Crazyflie 2.1. And so we just had our 10 years anniversary right in the middle of COVID, not so long ago. So we've been here for a little while. The Crazyflie 2.1, which is our main current product, is a small quad rotor with brushed motors. And one of the main characteristics is that the mechanical structure of the quad rotor is the PCB. That makes it very lightweight and very solid. It's very easy to work with because it's very hard to break. You're going to break motor mounts and stuff like that. Don't think we have ever broken an actual Crazyflie PCB, or very, very few of them, since Crazyflie 2 was released. And like I said, the firmware and software are all open source, and we're striving to make it as modular as possible and as modifiable as possible so that people can experiment with it and make new things and do some research. The ground ecosystem consists of 3 main parts. We have the quadcopter, the blocks now, the Crazyflie, and the boat, which is Crazyflie without the motors, which allows to make bigger quad. Positioning system. Some we make ourselves, some sell. Depending on how you define positioning, I think we have 4 positioning systems right now integrated into Crazyflie. That works pretty much out of the box. And the communication and software that assist the Crazyflie. So that's everything that runs on the PC and the radio doorbell that we made to communicate with the Crazyflie as well. In the Crazyflie, everything is written in C, and the main firmware is written with using FreeRTOS. And on the PC, everything we do ourselves in Python. So far, I'm kind of hoping I can rustify things a bit in the future, but for now it's Python. And ROS was developed by researchers using the platform, the ROS support, but now we're trying to internalize it more, trying to handle some of the ROS things ourselves as well, because from what we see in research conference, because that's platform that's used in research, it's 50-50 between the user of the Python lib and the user of ROS. The main board contains 2 processors, one STM32F4 as a main processor, so that's a main flight control, and 151, which is our radio communication processor. This implements mostly the low level radio communication and acts as a bridge, as a tunnel between the PC and the STM32. I want to point out that the firmware we run is completely custom. We're not based on, like we made it from, based on also a flight platform at Pixel. We of course have an AMU, maximum gyroscope, pressure sensor. That's very hard to use in this format, actually, but can work surprisingly well, actually, indoor. And the most important functionality of Crazyflie is the expansion board. Expansion board we call DEX, and we are making a branch of them to add extra functionality to the platform. So the idea is that the base platform is a flying platform, and then extra hardware functionality can be added modularly, both on top and bottom of the system. So we have DEX that bounce things like a lot, positioning, ultra-wideband, lighthouse, which is a steam VR positioning, ranging, LEDs. We have wireless chargers. When we go to conference, our demo always have this charging pad so that the Crazyflie autonomously land in charging pad and charges. So it means that we can make demo that runs autonomously. So relax. We're making a lot of these decks. Our customers are also making a lot of these decks because some of them are actually working on hardware projects, hardware researches, and that allows them to work successfully. So I've put like two examples of use case for the Crazyflie. One in research, that's a swarm trajectory planning research by James Price in USC, South California. They control a lot of drones and try to move them without them colliding each other and crashing each other. This is a nice example for communication because in that example there is a ROS framework called Crazyflie running on the PC and sending real-time set points to the Crazyflies, and there's a lot of them running at the same time. So our current communication stack is good enough for this kind of use case where we have a central node. And the Bosch board is an example of industrial use where Bosch has made a deck with basically all the sensors they could put in a single deck. There's like 6 packages of pressure sensor, gas sensor, and other MEMS gyroscope and accelerometer. And our understanding is that they are using that internally for demos, for demoing the different sensor on the flying map. And yes, one note is that MicroRos has been ported or running. There's a demo of MicroRos running in Crazyflie on the MicroRos website. And as far as I understand, this was pretty challenging to get working. And the core goal of the new stack would be to make this demo much easier to write and to make it work much better. So that is kind of the goal of this. We're not doing that actually for MicroRos, but the goal is that this kind of use case will become much easier in the future with the Crazyflie. So now for some communication history. So that's the very first Crazyflie quadcopter that was made in 2009. The motors came from toy planes glued on the PCB. I mean, I was flying PCB already back then. And we soldered it in a frying pan because we didn't know how to solder QFN. QFN was very scary back then. The gyroscope chip. But the use case in 2009 was one gamepad, one PCB position, and manual fight. So that's how the whole communication architecture has been designed. One Crazy Radio, which is a radio dongle, to one Crazyflie. And this has lasted quite a long time because at the beginning when we sold the Crazyflie 1, it was used for research, for researching flying a single quadrotor. So that was not a limitation. But around 2019, a lot more people, flying one quadrotor was pretty much sold. And a lot of people wanted to fly multiple swarms of them, centrally controlled. So the communication has been adapted to work with multiple drones. This was quite easy because we could just round robin communicate with all the drones rather than only with one. Crazy Radio was not optimized for it, so you lose half of the bandwidth, but it's good enough. And so it stayed like that. And we had some contribution to be able to reduce. This was solved by having more than one radio on the same PC to actually increase the bandwidth to the bands. And this lasted until the 2020s, where flying with centralized swaps was pretty much solved. I mean, people had done it. And then researcher wanted to do more autonomous flight, like running software in the flying platform and having autonomous communication from drone to drone and having them taking decisions together. So decentralized swarm. And that all falls down. I mean, this architecture completely falls down. We made proof of concept peer-to-peer functionality in the Crazyflie. So right now there is an API to send peer-to-peer packets, broadcast, and receive them. But if you do that, you do not have communication with the PCN. So in our demo, we usually use a Crazyflie connectable USB as a bridge to the Swarm, which is very suboptimal and really, really hard to work with. So that's really something that we want to address. And as far as I understand, this is also going to work pretty hard with the MicroPython demo. The current communication stack is organized like this. We have at the bottom the 2.4 GHz, 2 megabits per second radio. Our current radio has a hardware implemented packet handling, which is limited to 32 bytes packets, and this unfortunately creeps all the way up the stack. So that was a design mistake, that we have this 32 bytes limitation all the way up to the software. On top of that, we have something I call Safely, which is basically packet counters that guarantee that there's no packet lost, no duplicate packets when we communicate. And then we have CRTP, which is our application protocol. It's very simply a single packet header with a port, but the idea being that you have one port per subsystem in the Crazyflie, and it allows to map one subsystem Crazyflie to one driver on the PC independently. And that has worked fairly well. It makes the communication manageable and the implementation manageable. One problem though is that the packet format is free-form binary packets. Every subsystem implements slightly different format because they're not all made at the same time, even though most of them were made by the same people. Which means there's a lot of code to handle these packets. Some noteworthy subsystem for the Crazyflie are log and param. Param looks very much like ROS params. Log is a little bit more like topics, but it's done in a way where both for log and params, the user can very easily, in one line of C in the firmware, declare a variable to be logged or a variable that could be a param. And then on the PC, when we connect Crazyflie, we get table of content, log and params, and for log, we can actually request a composite packet of whatever value we want at such a rate. And this is used a lot for normal communication with Crazyflie, but also for experimentation. It makes it very, very easy to make custom code and to actually graph in our client. We can actually graph the values, so log variables. So that's very flexible. It's been used and abused time tools. Memory subsystem has been designed originally to access real memory, read and write to some addresses. We have an EEPROM and we have memories of the text. That allows plug and play detection of the text. It has been abused for subsystems. I mean, subsystems that had data that could not be transferred from log and param because single values float in, started implementing and memory space that could be shared with the ground. So that becomes, it works very well, but it becomes complicated to implement when you want to implement a new client or if you want to implement a new integration. I mean, most of the tools, for example, most of them are not supported in ROS and if they don't absolutely have to. And finally, I mean, it's a lot of special points, set points. Wherever we will need a functionality, we implement a new packet and we'll craft a new binary representation. So that's what we want to drive away from because it makes it very hard to implement. Like if you want to implement new ROS integration for the Crazyflie, it's a lot of code. The ROS integration has a lot of code to actually comply with this protocol. It's a lot of application because we also have that in Python website. So, the first step would be to have a new radio. So that is coming now. We have ordered the first batch of Crazy Radio 2 that will replace Crazy Radio PA. Crazy Radio PA is a very old chip that's based on an 8051. very fun to write code for, actually. It's a very ancient architecture, but also pretty hard because it's a very ancient architecture. And like I said, the radio is hardware controlled, so it's not flexible at all. You cannot do things with it. And it is not upgradable safely, so there's no safe controller. That was also a big mistake, which means that we've been very, very hesitant to release new software because if a wrong firmware is flashed, it's not possible to relaunch the bootloader, and then it's pretty much rigged until someone has a SPI programmer to report it. So we've been pretty stuck in functionality with that. Because of that. The new Crazy radio is based on NRF52. Has a lot of RAM, more RAM than the Crazyflie. It's insane. Much more powerful CPU. The radio is much more flexible, so you can actually start implementing the radio protocols, and it has a safe control. So, and a nice one actually that actually shows up as a disk to it. So this will allow us to improve it over time. And when new use cases arise, we will be able to update the radio to actually implement new use cases. And talking about radio protocol, we are planning on implementing 2 new ones. There's been a lot of thought about this peer-to-peer actually, and the current decision is to implement 2 independent protocols. One channel hopping one, which would be the star network like we have right now, where the assumption is that you have one PC, couple of Crazy radio connected to a couple of Crazyflies. This is to ensure low latency and high bandwidth, to maximize the bandwidth, and channel hopping will be very similar to Bluetooth technology, but with latency. Should be a much safer link than what we have right now, much more reliable. And peer-to-peer, so the kind of decision is to have that as a separate protocol, because doing channel hopping in peer-to-peer is going to be really, really hard, and synchronization everything is going to be really, really hard. So this is going to be a carrier sense kind of network where everyone can talk at the same time, and it makes sense here to find out if no one talks about right now, and if they can send packet. This means that the latency will be much less. In most cases it will be okay, but in some cases the packet can be delayed quite a lot. And bandwidth also much, much less. Must stay below like 30% occupation of the air. Otherwise you have big troubles with latency. One big advantage though is that Crazy Radio 2 will be able to be a peer. So that will be part of the design. So having, and I'm thinking about the MicroPython use case here, having a use case where you have multiple PC. Crazyflie will be possible. And we're not planning on this right now. If anyone wants to do it, please do, but I think right now my feeling is that this is too hard with not a lot of benefits for our current use cases. It could be done later. It could be done. And for the communication stack, the plan is that I started with well-specified testing and observable layer. I'm a bit frustrated that every time right now we have a problem with Crazyflie, everyone's always blaming the communication. They are not always wrong, but we lose a lot of time because communication right now is a black box. So when we have prime, we blame it, and we cannot really measure it to understand if it's really the case. So having it observable is very, very important to me. And the plan is to base the new communication over an RPC layer, remote pseudocode, and essentially the Crazyflie firmware will be seen as a branch of functions, like an API, which means that we can document it really well, and which will fit really well in framework like ROS. The RPC layer I'm planning on using is also supporting notifications, so sending packet without an answer back, which would fit very well with implementing topics, for example. You can map directly a function called ROS service. So one of the goals is to have our libs and the ROS implementation much thinner, much less code, much less things to handle, so it will be much easier to keep it updated. I'm hoping to have no arbitrary MTU on the transport, so to have packet as big as possible on the top, independently of the bottom size. Let's see if that happens. The new radio already have much bigger packet. I don't like having this limit. And multi-connection handling. This is also something we do not have right now, but it's very necessary to start talking about peer-to-peer networks. So from the get-go, we will be able to connect multiple clients to the same Crazyflie, which is not a use case right now that we support. It's not been designed like that at all. And the nice thing with this RPC is that this is just a branching function. This could be used from within the Crazyflie. So the idea is that a MicroROS implementation with this new architecture would just be a new connection to the RPC. It doesn't necessarily have to pass through CBOR or FLIR. It could be a direct function call eventually. You can always optimize things, but that will simplify a lot making application in the Crazyflie, because we have this nice application framework where people can actually have an application in their own Git repo and use Crazyflie as a dependency, and then they will build a Crazyflie kernel with their app. But right now the public API is different if you're running in the Crazyflie or if you're running outside. Here we have an opportunity to have the same API for both use cases, which will make development much simpler. Will make it more clear what you can call and so on. And finally, that's a bit of a crazy thing, but I think it has potential. RPC could also be expanded to expansion board. Our DEX starts to be much more complex. The latest one is the AI deck, where we have a camera, an AI optimized microcontroller, and ESP32 for Wi-Fi. That's very time consuming. So in that example, if we would say like we have a clever LED rig in a set color, once it's connected to Crazyflie, there's Crazyflie A. I'm an RPC and I implement these functions. Crazyflie would mount the RPC under dex.led. So an app running in the RPC could call dex.led.setColor and would be routed to the deck. And even further, when Crazyflie connects to Crazy Radio 2, it would tell, hey, I have an RPC, and Crazy Radio 2 could handle the connection by itself, and mount the deck and the Crazyflie and their CF0. So someone that don't know anything about the decks, that doesn't have the driver, say a ROS node, would actually call the Crazyflie.call RPC CF0.dex.led.setColor and actually set the color of the deck without implementing any special case driver in on the PC side. Know that you might want some nice APIs on top of your decks, but at least they will be reachable, which means that the deck designer will not have to modify everything and will have access to all the decks, which is not really the case right now because it requires special development. Yes, that's it for me. Thank you very much. Is there any question?
Yeah, I have one. Is the new principle compatible with the Bitcraze or
No, it's gonna be compatible in multiple ways. We will ship it. We couldn't decide, so we will ship it with firmware that's compatible in both sides on software. And because I have a new USB bootable, we will ship it in bootable mode, and there will be one firmware compatible with the old USB bootable firmware with the new USB bootable. And the idea being that we go forward with the new USB protocol, and later down the road have a new radio protocol. That's all. The radio in the Crazyflie is already flexible enough to deal with more advanced communication radio protocols.
because at some point we will need a new Crazy value and we can use the expression.
Exactly.
Cool.
And just to note, the NRF24 is not going to be available for private. So if you want new Crazy Radio, it's going to be Crazy Radio 2. It's a competitive channel. Very soon.
I have a question regarding the control of the Crazyflie. So I'm assuming correctly that runs the control algorithm itself runs on the Crazyflie.
Mm-hmm.
And on which frequency does this run?
You mean the stabilization control?
Mm-hmm.
I think we have to runs at 100 Hz rate.
Something like that.
100.
That's the status matter. The attitude controller is at 500 Hz. So twice as slow as the actual ticks of the STM, and I think the position controller is either 200 or 100 Hz. So like it's a 4 times cascaded PID. we have 4 controllers now on the Crazyflie. I think, is it 4? Yeah, it's 4. Like it's PID, and then we have manager controller, and then we have IDI controller, and the new one that I forgot the name. Last year it's experiment.
Yeah.
I don't know. Sorry.
Yeah. So my interest was, I guess this is running then in some dedicated thread, I guess, on FreeRTOS.
Yes.
And the question would be, on as you say, we would run then MicroROS on the Crazyflie. You could also use, or that would be a question, is there any, do you see any benefit in having, let's say, a real-time executor that would allow you to run this as a callback or as a timer callback in MicroROS? Or do you say, okay, we are completely fine running our control algorithm and our own loop in our threads? Because I'm kind of working also in ROS2 to design a new real-time capable executor in ROS2 and also in MRCLC. And then of course there's a use case where we want to demonstrate, right? I mean, what's kind of the latency, what's the jitter, and so on. And I thought, because you're developing the Crazyflie, which has high requirements on real time, how you're doing this at the moment. And are you fine with your solution at the moment, or do you see benefits if you could use ROS there as a central framework as well, or do you say, okay, we are fine at the moment and we just use MicroROS or ROS for communication? You're getting new set points from the PC and handling just the communication.
Arnaud, do you want to take this? Or,
yeah. This is not something we've thought about at all. I think we've been seeing ROS, MicroROS, as mostly as a communication layer so far. And like I said at the beginning, 50% of our users are not using ROS at all. But if I understand what you're saying correctly, it would be possible to use ROS as a running front, as an executor, even though you might not even use ROS as a communication layer.
Yeah. So I mean, you can have your timer, right? I mean, you could have a timer that runs with 100 Hertz to 100 Hertz or 500 Hertz, and then you will have your callback in there, and that would be the command, right? I mean, the control algorithm essentially, and then you would have, let's say, one framework where you're designing, where you could design your entire application, and you don't have to, when you have communication coming in ROS framework, then I guess you need to have some exchange to information to your local threads, right? So you need to guard it with some indexes and stuff. I was just wondering what your is there.
Can I comment also on this? I guess like it's if you would, because of course we maintain the Crazyflie and we have our internal firmware which we use a lot. But if you just look at the users that use the Crazyflie, they try to kind of tweak the controller on different levels as well. So, for instance, that they would rather want to, for instance, that's one of the support questions that we get quite a lot. If they want to do like an off-board controller and just control directly the RPMs on the Crazyflie. Of course, in terms of delay, if they want to do off-board control, that is going to be a bit more difficult. But there's definitely a lot of control engineers are using the Crazyflie to kind of rewrite controllers, let's say, and if they can do that from, for instance, like MicroPython, to have that in direct, let's say the direct control on that. Perhaps not within Bitcraze, where perhaps we're not going to use it ourselves. But I definitely think that users that use the Crazyflie or researchers that use the Crazyflie might be very interested in that. I would say, yeah, and mostly in the control engineering.
I mean, what I'm thinking about is like a perfect development platform to test this kind of real-time capabilities of this kind of executor. Like you say, I'm not sure we would do that ourselves, but this is interesting. We definitely look at it.
I must say that one of our colleagues did try to lower the rate of, I think, the attitude rate controller from 500 hertz to a lower amount, and it was still able to. It was a little bit wobbly, but it was still possible. So you don't have to run at 500,000 hertz. So, yeah.
Yeah, but I'm just saying, I can run something with 500 hertz with the local function. You can also do it with the MicroPython framework.
Yeah.
There's not much overhead, and there's also ways to prioritize then this callback, so they are not, in the normal, sequential execution of all callbacks in ROS, but you could prioritize your 500, frequency callback, and then you will definitely. You're sure that you can maintain this frequency. Yeah. Okay, cool. Yeah. I'll let you know when.
Yeah, that will be really cool project.
Some update on this, and would be great to know that it's going to be a potential test. Yeah.
Okay, so thank you very much to Arnaud and Kimberly. And well, this is everything for today. I hope to see you next month here.
Thank you.
Thank you
for inviting us.
Bye.